Okay, so let's take a look at the solutions to these projectile motion practice problems to help get you ready and prepared for that projectile motion test. These are the same problems that I went over with you in class today, but this is a way that you can kind of back up and maybe you can use these as a reference to help do some extra practice if you need it in order to be able to perform better on the test, which is going to be given back to you tomorrow. So this is number one, and we're going to do two sets of problems, one where we've got horizontal launch and then one where we're something flying through the air. So first of all, here's my diagram. I got a cliff and I got somebody who looks like pushing something that's a soccer ball and it's kicked and it has an initial velocity of 20 meters per second going this way. It's horizontally. In other words, it's flat. It's only in the x direction. It's not going up and down at all. It is horizontal. So what is the initial y velocity of the ball? Well, if it's launched horizontally, it's not going up and down to start. The initial y velocity is 0 meters per second because this word horizontal means that it is totally flat, at least at the start. It's not being thrown up or down at all. It is being thrown horizontally. What is the x acceleration of the ball? Remember that an acceleration is a change in velocity, whether it speeds up or slows down or changes direction. Well, there has to be something that causes an acceleration. And in the x direction, once the ball leaves the player's foot, the player has no more control over it. The player can't make a ball speed up halfway through its flight. Therefore, there is no x acceleration. And this is true of all projectiles. There's never going to be an x acceleration because once it starts going through the air, there's nothing to make it speed up going this way. That's an important point to remember. There's never going to be any x acceleration. Now, we start to get to some calculate how long it takes the ball to hit the ground. This is going to be a calculation for which we are going to need our kinematics formulas. Now, I write mine a little bit different, but they're all the same. I prefer the d instead of the delta x or delta y because it's 1d. It's a distance. It doesn't really matter. But I wrote it both ways just so you can kind of see and how it's familiar to you and how it was presented, maybe how the formulas are in the test. Also here, we've got a velocity at some point is the initial velocity, which I believe you guys have used v naught. It's the same thing. I like the I because it makes sense to me. Initial versus F for final. A is an acceleration, T is a time. Here we've got that distance thing, a distance either in an X or it could be a distance in a Y. 1/2 my acceleration, time, there's my initial velocity, time again. So we've got these formulas and I want to calculate, and this problem was very specific. It said to calculate how long. We want to know a time it takes the ball to hit the ground. Well, the ground is down here. So we want the time for it to move from here to this point because that's where the ground is. So we're talking about the motion in the y dimension. We're not talking about the x here because we're talking about how long does it take for it to go down to hit the ground. So I need a formula that has time in it that will work in the y dimension. Now, I've got this formula here. It's got a time, it's got a velocity, and it's got a distance. This one will not work for me because this formula is only if there is no acceleration. Notice all of these problems here, they have an acceleration. These problems account for an acceleration. This one takes no mind of an acceleration if there is one. And you have to say to yourself, think about this conceptually. Is there an acceleration of this ball as it moves from here to the ground? Well, sure it is. There's free fall involved here. This ball is in free fall. It's being accelerated from here to the ground by gravity. Otherwise, it would just keep on going in a straight line. So I need a formula that has something to do with time, but also accounts for that acceleration. Okay, let's take a look here. Well, what am I given in the problem? Do I know anything about any velocities? I know the initial y velocity was 0, but I don't know a final y velocity. Do I know a distance involved with it moving to the ground? No. I know the distance it's going to move to the ground is 50 meters. So that might work for me. My distance is 50. I know my acceleration caused by gravity is negative 9.81 meters per second squared. There's what I'm solving for. My initial y velocity is 0, which is going to make that whole term. So I'm liking this formula. I think it'll get me what I want to know, which is time. So I'm going to say d equals 1/2 a t squared. Now my distance is 50. 1/2, the acceleration is negative 9.81 meters per second squared time squared. And then I can solve for this and I can get a time. And I won't necessarily go through the math here. I will pause this, do the math on my calculator, and then we'll write down an answer. See if you get the same. When I did the math, I got a time of 3.2 seconds. That's how long it takes the ball to hit the ground. Now keep in mind, the whole time it's falling, it is also moving forward. So what's the final velocity, final x velocity of the ball? Well, there is no x acceleration. Does it have an x velocity? Well, it started off at 20. There is no x acceleration, which means its x velocity is going to be the same the whole time because there's nothing speeding up or slowing down. So the final x velocity is going to be 20 meters per second because it doesn't change because there is no acceleration in the x dimension. Calculate the final y velocity of the ball. Does the y velocity change? Well, yes, because it starts off at 0 because it was launched horizontally, and it's going to speed up as gravity pulls it towards the ground. This is a calculate problem. So this is a situation where we want to actually find a kinematic formula that's going to allow us to find or solve that final y velocity. So let's find all right, here's a velocity formula. We'll start off simple, and if we have to, we'll get to the more complicated ones. My velocity is the initial velocity plus the acceleration times the time. Do we know how long or the time it took to hit the ground? Sure, we just found it out. It was 3.2 seconds. Do we know the acceleration as it's moving to the ground? Yeah, it's negative 9.81 meters per second squared. Do we know what its starting speed was? Or starting velocity? Well, in the y, it was 0. Remember, we can't use 20 here because that's in the x dimension. So I'm going to use this formula. V equals the initial velocity plus acceleration times the time. So my initial velocity in y was 0. My acceleration is negative 0.981 meters per second squared. And I know my time is 3.2 seconds. So now let's pause, punch the numbers in the calculator. Let's see what we get. Well, I got 31.39 meters per second. That's my unit of velocity. So that's how fast the ball is moving that way when it hits the ground. That is the final y velocity. Now, calculate how far from the cliff the ball lands. We want to know this distance. That's a distance in the x dimension. That's a distance in the x, not in the y. We know the y was 50, but how far did it move this way before it impacted the ground? Well, let's find a distance formula. Once again, we'll start off simple. Distance is velocity times time if there is no acceleration. Well, we're looking for a distance in the x dimension for which we know there is no acceleration, so I can use this simple formula here. The distance is the velocity times the time. Well, the velocity was 20 meters per second because that's what it was launched horizontally with the speed of. The time we now know is 3.2 seconds. And when I do this, it's going to be what? 3 times 20, 60.6 meters. So the ball lands 60.6 meters away from the base of the cliff. Now, back to a concept question. When this ball impacts the ground, does it have an x velocity, a y velocity, or both? We just said it's moving down with the velocity of that when it hits the ground. It's also moving forward with the velocity of that when it hits the ground. So it has velocity now in x and y. It has velocity in both. Okay. Now, the start, it only had x and had 0 y. But now we've got two different velocities, and the combination of those two velocities is what we call the resultant velocity. Because we can't say that this ball just has x velocity or just has y, it has both. And we find a resultant like this. Think about it as a triangle. My x velocity, we know, is going this way. My y velocity is going up and down. Well, when we take two vectors and we add them together, we get what's called this resultant. And that's the velocity of the ball as it's moving along its path. Because it's not just moving in x, it's not just moving in y, it's moving in both now at the same time. And for that, we use our trig to determine the resultant velocity. So my x velocity at impact is 20. My y velocity at impact was 31.39. And I can use my SOHCAHTOA to find out what this, well, actually, the hypotenuse is easy. I can do a squared plus b squared equals c squared. That's no worries. I'm going to do that real quick on the calculator. When I did my a squared plus b squared equals c squared, I get a number of 37.2 meters per second. That's the resultant velocity. And it should be the bigger number, right? Because the hypotenuse is going to be the biggest value in a right triangle. Now, the direction. When we talk about velocity, we're talking about both speed and direction. So we know it's going this fast. That's its velocity. That's really its speed. But which direction is it going? It has an angle that it is moving at. It's some angle up or some angle down. In this case, it's an angle down because it's going down to the ground. We want to know what this angle is. So I got this angle. I want to know what is that angle? I use this sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, or tangent is opposite over adjacent. Because I know all sides of the triangle, I can use any one of them to figure out what that angle is. So the sine of my mystery angle is going to be the opposite 31.39 over the hypotenuse, 37.2. Okay, that's just a math problem. I can do those numbers. So when I divide those two, I get 0.843. So the sine of my angle is 0.843. Then I can do the inverse sine. That'll give me the angle. And I hit inverse sine of 0.843. That will tell me what the angle is. When I do that math, I get about 57.5 degrees. That's my downward angle. So the resultant velocity is 37.2 meters per second at a downward angle of 57.5 degrees. So now back to some concept questions. What would be different about this if the soccer ball was twice as heavy, but let's say the guy can still kick it at 20 meters per second? Where did weight come into any one of these problems? Obvious answer is it didn't. Projectiles are not affected by their weight. All things fall at the same rate because gravity is the same on everything. So what would have been different? Nothing. A shot put in a ping pong ball theoretically launched from the spot together. If they have the same initial speed, they'll both hit the ground at exactly the same place at exactly the same time. Now, what would have changed if the ball had been kicked with an initial horizontal velocity of 35? We're not going to go through all the math here, but this is a thinking question. What would have been different if instead of 20, we made this 35? Well, what wouldn't have been different? If we go back up to the time formula, notice in the time formula, we were solving for the time in the y dimension. This is an x velocity, has nothing to do with the y dimension. So therefore, doesn't matter how fast we kick the ball, it's going to take the same amount of time to hit the ground. So what would have changed? Not the time. It would still equal, what did we find? It would be 3.20 seconds. But something would be different. If it's still falling at the same, it still takes 3.2 seconds to hit the ground, it doesn't mean it's going to land in the same place. Because if you kick it faster this way, it's actually going to cover more distance this way in that 3.2 seconds. So the x distance increases. Because if I kick it faster, it's going to go further this way before it hits the ground. If my initial velocity were slower, I don't kick it as fast, it's not going to go as far. Still going to take 3.2 seconds to hit the ground, it's just not going to go as far before it hits the ground. Now, what would have changed if the cliff were 75 meters high instead of 50? We're not going to go through and do all the math, but let's just talk about theoretically what would have been different. Where did the height of the cliff come into play? We used it right here when we solved for the time. If I put in a bigger number for the height of the cliff, my time is then going to be bigger. It takes longer to fall from a higher cliff. So, cliff gets higher, the time's going to get bigger. Now, if it's moving for longer, the x distance is also going to increase. Even though the x velocity stays the same, it's moving for a longer amount of time. So it's going to end up going this way further if the cliff were 75 instead of 50. What else would be different? The y velocity would increase. It's going to hit the ground faster if it falls from a 75-meter cliff than if it does from a 50-meter cliff. So let's take a look at the second problem. The second problem is similar but different. Same thing. This time we got a cannon launching a cannonball off of a known height of a cliff. This time we know where the cannonball lands. What we don't know is how fast it started with. So we're going to kind of work backwards and figure that out. First thing we're going to do is calculate. Well, that's a formula here. How long was the ball in the air? We want to find the time. Well, what determines the amount of time a projectile in the air is gravity. And gravity has that same acceleration of 9.81 meters per second squared. And the distance that it falls affects or determine how long it falls or the time it takes to fall. Makes sense. It takes more time to fall from a higher building than a shorter building. So I can use this distance to calculate a time. I know what distance it's falling. I know the acceleration. I want to find the time. I know the initial speed in the y direction is 0 because I was told once again that it was fired horizontally. So I can use that formula. The distance is 1/2 the acceleration time squared. Well, what distance did it fall? 15 meters. So 1/2 the acceleration is negative 9.81 meters per second squared. This is time squared. The initial y velocity is 0. So that's nice, so it cancels that out. Now all I've got is one unknown variable, and I can solve for the time. So I solve the math, and I get 1.74 seconds, which kind of makes sense because this is a much shorter cliff than the one we had in the previous problem. In the previous problem, it took 3 seconds to fall 50 meters, so yeah, it makes sense. 15 meters, it's going to be a much shorter amount of time. Okay. Now, was the initial velocity in the cannonball in x, y, or both? It was only in x because it was fired horizontally. It wasn't aimed up and down, so there was no initial y velocity. Now it says calculate the horizontal velocity. Well, this is a math problem. So let's see. I got a velocity here. This is horizontal, which means x, which means no acceleration. I can use this for the x. Do I know the x distance? Well, yeah, the guy watched it and figured out it landed 20 meters away. I don't know the x velocity. That's what I want to solve for. I know how long it was in the air at the time. So I can use d equals v times t. I know the distance it moved was 20 meters in the x. I want to know the velocity in the x. And I now know the time is 1.74 seconds. So solve for this, punch numbers in my calculator. When I do that math, I get 11.5 meters per second. So that's how fast it came out horizontally. Now calculate, once again, to calculate the y velocity when it hits the ground. Initially, the y velocity is 0 because it's not going up or down. But when it hits the ground, it is moving in the y direction. So to calculate the downward y velocity, let's look at our kinematic equations and see what can we use. I can't use this formula for y because this is a no acceleration formula, and I know there is acceleration in the y dimension. Okay. To find acceleration in y, take the initial y velocity, which was nice because we knew it was 0. The acceleration in the y is 9.81, and we now know it was falling for 1.74 seconds. This works. So the downward velocity is equal to v initial is at. So my y velocity is 0 because there was no initial y velocity. Negative 9.81 meters per second squared, and a time of 1.74 seconds. Multiply those two, and I'll get my answer. When I crunch the numbers, I get 17.1 meters per second. Now, the resultant, remember, that's the combination of the two. That's my x velocity, and that's my y velocity. Well, my x I had figured out was 11.5, and I know my y is 17.1. So my resultant looks something like this. I do a squared plus b squared equals c squared. The magnitude, or the number part of my resultant velocity, is 20.6 meters per second. But remember, velocity is a vector, so we need to describe the direction. We need to say what that angle is. How much is it aimed up or down? Once again, I can use the sine of my angle that I want to know is the opposite, 17.1, over the hypotenuse is 20.6. So that's going to be that sine equals whatever that number is. So that number was 0.83, so the inverse sine of that, I get an angle of about 56 degrees. So my resultant velocity is 20.6 meters per second at a downward angle of 56 degrees. So back to a concept question. What could be done to make the cannonball hit a target that's 50 meters away from the cliff? Well, if we wanted to move farther this way, what I would have to do is increase my speed or my x velocity so that it goes farther before it hits the ground. Now, can you increase the time? Well, not from right there, you can't. You might be thinking, well, if I want to increase the time, maybe that's as fast as the cannonball can fire. If I built a higher tower on top of this cliff and I launched the cannonball that way, it would go farther because now it's higher and it's going to be moving for longer. So once again, you have this as a reference. You can email me with any questions or things you didn't understand, and or come see me in the morning before we get that test back tomorrow. At this time, we're going to move on to, and we're going to do a little bit more complex example of projectile motion.